Hello and welcome to the Maths 2 component of the online BSc program on data science and programming. In this video, we are going to talk about differentiability and the derivative. So, let us start by first recalling the idea of the rate of change. Okay, let us do this example of a truck which is travelling from Jalandhar in Punjab to Trichy, Tiruchirappalli in Tamil Nadu. So, the distance is about 2900 kilometers and it takes the truck about 72 hours to get there. What is its speed? So, I'll give you a second to think about that. Let me repeat the question. What is the speed of this truck in kilometers per hour? So, if you have thought about this, I think most of you would have done the following. You would have taken the distance covered, which is 2900 kilometers, and divided by the time taken, which is 72 hours. So, you would say that the speed is 2900 kilometers by 2900 by 72 kilometers per hour, which is I guess about how much would that be? About 1 by 2.5, which is 4 by 10, so 0.4. So, 0.4 into 100. So, that means this would be about 40 kilometers per hour. So, I think if you have done your computation, this would be about 40 kilometers per hour. Okay. So, after reaching Trichy, the driver tells his friend that he was fined by a traffic constable near Nagpur, Maharashtra. So, if you look at Google Maps, the route will go past various important and interesting places like Agra and Jhansi and so on. So, it will pass via Nagpur and Hyderabad and so on. So, near Nagpur, this traffic constable stopped the driver and he was given a fine for speeding. By the way, do you know what the speed limit on Indian highways is? Probably not. You should go and check that out. Fine. So, the friend calculates his speed from the above data and says that the constable is wrong and that the fine was unjustified. So, what does the friend do? They do exactly what you probably did. They do 2900 by 72 and compute that the speed must have been 40 kilometers per hour, and they say, hey, how can that be speeding, right? So, indeed the high speed is above 40 kilometers per hour allowed. Okay. Is the friend correct? So, from this information, can we really conclude that the speed of the truck whenever the traffic constable stopped the driver was 40 kilometers per hour? I think you probably will agree that the answer is no. The driver then mentions that he covered the 260 kilometer stretch in Maharashtra. So, when they pass through Maharashtra, it is about 260 kilometers. They enter from Madhya Pradesh and they exit into Telangana and then close to Hyderabad, or after some time they hit Hyderabad. Okay. So, the driver mentions that he covered the 260 kilometer stretch in Maharashtra in 4 hours with about an hour's break for breakfast. Okay. So, in 4 hours the truck has travelled 260 kilometers, but out of those 4 hours 1 hour was spent on breakfast. So, that means in 3 hours the truck covered 260 kilometers. Aha. So, now we have a different data. As you know, Nagpur is in Maharashtra, and now that means within Maharashtra the truck was travelling at a much higher speed than the rest of the journey. So, what was the speed there? If you calculate, you will probably have gotten 260 by 3 kilometers per hour, which would be what would it be? Something beyond 80 kilometers per hour, something beyond 85 kilometers per hour, maybe something like 86 kilometers per hour, which is well above the speed limit. The friend now recalculates and takes back his opinion that the fine is unjustified, right. So, the friend does exactly what we did, that the truck is probably travelling at 86 kilometers per hour. Well, the constable is justified in fining the truck driver. Is the friend correct now? So, what happened here? we initially knew that the truck travels the entire distance from Jalandhar to Trichy which is 2900 kilometers in 72 hours. We computed that the speed is 40 kilometers an hour. Then we have this new set of information that within Maharashtra the distance was 260 kilometers, which was travelled in about 3 hours, 4 hours, but with an hour's break for breakfast. So, which was about 86 kilometers per hour, or maybe more than that. The friend says that okay, then maybe it is correct that you are fine. Is that correct really? So, if you think carefully, the same argument that applied for the first case, meaning if you felt that the friend was incorrect in the first place, then you would agree that the friend is also incorrect in the second place. And why is the friend incorrect? Because you cannot really say what speed the truck was going at exactly when the constable fined the truck driver based on the average speed, right. So, the speed can increase or decrease, right, as you go along. So, that is why we have the speedometer, and as we go along the speedometer increases and decreases, it tells you how much the speed is. And the instantaneous speed, which is what the speedometer shows you, cannot be calculated from saying that oh, I travelled this much distance in this much time. So, the take home from this example is that the average speed and instantaneous speed are different concepts, and one cannot deduce the instantaneous speed from the average speed. Okay. You may be able to give some heuristic, but remember it is only a heuristic. It cannot the average speed and the instantaneous speed are totally different concepts. So, for the instantaneous speed, how do we get that? Well, we really have no way of getting that from the information given. For that, if there was a camera on the dashboard or behind the truck driver capturing the journey, specifically the needle etc. for the speedometer, then from there we may have been able to get it, right. But unless you really kept track of the entire journey, there is no way of getting it from the data given. The average speed, different ball game, we could compute that based on the data given. Okay. So, the constable may have had a speed gun. Of course, this is not maybe so common in India, especially on national highways, but they could have had a speed gun, and typically what happens is if they have a speed gun and they have pointed it towards the vehicle, they know instantaneously what speed the vehicle is going at. Okay. So, that computes instantaneous speed, fine. So, to calculate instantaneous speed at some time, what do we need? We have to compute the distance travelled in a very short period of time around the time that we want to calculate it at and divide by that period of time. Okay. For example, you could take the distance travelled in 1 minute after that time. So, if you have travelled y kilometers in 1 minute, then the instantaneous speed would be approximately, and again the underlined word here is approximately 60 y kilometers per hour. Why approximately? Well, even this is not instantaneous, right. Within 1 minute the speed can vary so much, right. Maybe within 1 minute there was a series of speed breakers, or a mountain side started, or there was an accident and the driver slowed down, or they just stopped for chai, anything, right. So, even 1 minute could be too long. So, this is just an approximation, only we may feel intuitively that it is a better approximation than the speed computation based on the entire journey duration. Okay. So, ideally what would you do? You take as small a time interval as you possibly can, and mathematically we would call that an infinitesimal time. So, when you keep taking smaller and smaller times, this is really what you are saying is, well, let my time shrink, the time interval I take, that shrink to 0, and that is exactly what we know is underlying a limit. So what exactly is instantaneous speed? You take the distance travelled in time delta t. So suppose you want to take you want to know the instantaneous speed at a particular time t0. So you take t0 plus delta t, take the distance travelled within that time, between time t0 and time t0 plus delta t, and divide by delta t, and you let limit delta t tend to 0. Now of course you have to measure this correctly, because if you want it in kilometers per hour, then delta t has to be measured in hours and distance has to be measured in kilometers. So even if it is, you take delta t to be 1 second and distance is 1 meter, you should think of that as 10 to the power minus 3 kilometers and 1 by whatever 3600 hours, right? And then that's how you should calculate. That is how you will get instantaneous speed as a limit. And this is really why, one of the main reasons why we are interested in limits in the first place, because limits are really at the heart of things like instantaneous stuff. Okay, for example, instantaneous speed. Okay, so now we can extrapolate this and we can talk about the rate of change. After all, what is speed? Speed is the rate of change of so how much distance you covered in time. So the rate of change, right? So that concept is called differentiability. So let f be a function defined in an open interval around a. So a is a point. Then f is differentiable at a if limit h tends to 0, f of a plus h minus f of a divided by h exists. Yeah, this is exactly the kind of idea we had before. In the previous slide, your f of x plus h minus f of x. So f was the, f represented the distance covered. So x was the time. So f was a function of time. So if you wanted the instantaneous speed at time t0, we would have written this as f of t0 plus delta t minus f of t0 divided by delta t. So the delta t here is replaced by h and the t0 is replaced by a. So this is this limit, we say that the function is differentiable at a. Okay, and what is this limit doing? If indeed it is differentiable, then this limit is computing for you the instantaneous rate of change of the function, right? So the rate of change of distance with respect to time is exactly the instantaneous speed. So the rate of change of any function f with respect to this variable x, that is what this limit is computing. Okay, let's look at these two examples. So f of x is differentiable at a point a. Why is that? Let's do this computation. So if you do limit, let me do this explicitly. So limit h tends to a, f of a plus h. So what is a here? A is any point. This is what we want. What is my function? My function is just x. So this is limit x tends to 0. F of a plus h is a plus h, and f of a is a. So a plus h minus a is h. So this is limit h tends to 0, h by h, but h by h is 1. So you have limit h to 0 of 1. So now if you take the limit h tends to 0 of the function 1, this is just 1, right? So what are we saying? If you take f of x is x, the rate of change of this function is 1, right? This is not a very difficult fact to appreciate. It's changing by, if you take 1 unit, then it's changing by 1. Yeah, so this is more or less what it's saying. Let's look at f of x is sin x. So if at the point 0 now. So this is f of 0 plus h minus f of 0 by h. So this is limit h tends to 0, sin of 0 plus h minus sine of 0 divided by h. Aha, but what is this? This looks like something familiar. So, the first term is sine of h, the second term, meaning the second sine value is 0 because sine of 0 is 0. So, sine h minus 0. So, I will just write sine h then divided by h. So, now this is the limit of h tends to 0 of the function sin h by h, and in the previous video we have given a very detailed argument to show that this limit is 1. So, sin x is indeed differentiable at the point 0 and the value of the limit is 1, okay. And we are going to say more about this as we go ahead. So, I hope these two examples tell you how to compute. So, when you take this limit h tends to 0, we have converted this function f to a function of the variable h. So, remember that when you compute this limit, you have to think of this entire expression as a function of h. Okay, so let us do a couple of other examples. So, f of x is mod x is not differentiable at 0. So, indeed this was one of the places we were stuck at vis-a-vis tangents. F of x is x to the power 1/3 is not differentiable at 0 and f of x's floor function is not differentiable at any integer point. So, let us do the first one. If you take f of x is mod x, what happens? So, at 0, let us take the limit as h tends to 0, f of 0 plus h minus f of 0 divided by h. So, this is what we want to compute. Okay. So, what is your function? We want to compute the limit h tends to 0 of the function. So, f of 0 plus h is f of h, which is mod h minus mod 0 divided by h. So, limit h tends to 0 mod h by h. Okay. So, now we have to look at the function mod h by h and ask what is its limit as h tends to 0. So, what is the function mod h by h? So, mod h by h is just the function. So, mod h by h, well, what is this? So, if h is positive, then this function is just h by h, which is 1, and if h is negative, then so this okay, I should write. So, this is h is strictly greater than 0. And if this function is if h is negative, then mod h by h is minus 1, right. So, this is what it is, and of course, it is not defined a priori when h is 0, but anyway we want to only compute the limit as h tends to 0. So, now we have to compute this limit as the left hand and right hand limit, right. So, this limit exists. First of all, we have to ask what happens to this function from the left. So, from the left you can see this is minus 1, from the right you can see this is plus 1, and hence this limit does not exist. Okay. And once this limit does not exist, that means the function is not differentiable at 0. Okay. What happens to f of x is x to the power 1/3? Why is this not differentiable at 0? So, let us write down what this limit is. Okay, so let us again do this from first principle. So, this is h to the power 1/3 minus 0 to the power 1/3 is 0 by h. So, this is h to the power 1/3 by h to the power minus 2 by 3. This is what we get. Okay. So, now what happens to this function? So, for this function, as h tends to 0 from the right. So, again we have to ask what does this function look like. So, okay, maybe I should write this more explicitly as 1 by cube root of h squared. Okay, this is what the function is, in case it is confusing you, what the minus 2/3 is. Okay. So, you take h, you square it, then you take its cube root and then you divide by that. So, you can see as h becomes h is positive and h is small, meaning it tends to 0, when you divide it is going to become very large. So, the this limit is going to diverge to infinity, okay, or does not exist, whichever you prefer. Okay. So, I will say does not exist, as in diverges to infinity. This is exactly the behavior that we encountered for the limit 1 by h. So, this is similar, and similarly if you take from the left, the same thing happens, it does not exist, which is to say it diverges to infinity. Yeah, again the same behavior as we saw for 1 by h, and because of that this limit does not exist. So, the function is not differentiable and 0. Okay. What about f of x is floor function of x? This I think is very apparent that there will be a problem, but let us do this computation anyway. Let me do it for 0, but the same argument holds for any integer. So, for 0 what do we get? Floor function of 0 plus h minus floor function of 0 divided by h So, floor function of h, so floor function of 0 is just 0 and then this is divided by h. Okay. So, now we have to ask for the limit from the left and the right. So, what is this function? So, this function is going to be 0 if h is between 0 and 1, and it is going to be minus 1 by h if h is between minus 1 and 0. So, I hope this is clear. And what happens? So, now if you take the limit from the right, so this limit is 0, but the limit from the left is undefined, right. This is minus of minus 1 by h, and we know that this is does not exist. So, this actually diverges to plus infinity. Why plus infinity? Because we have a minus 1 by h. So, if you had 1 by h, it would have gone to minus infinity. Because we have a minus 1 by h, it goes to plus infinity. So, in any case this does not exist. Okay. So, all the results that we have proved in the previous or seen in the previous videos have now come to help us in checking whether a function is differentiable or not for these elementary functions. Let us put that last example in a more general context. Differentiability implies continuity. So, if f is differentiable at a, then it is continuous at a. So, why is that? Let me sketch out the argument. So, we want to say that limit x tends to a of f of x. We want to conclude that this is equal to f of a. Okay. What do we know? We know limit f of x plus h minus f of x divided by h. So, we know that this limit exists, and so let us call it L. So, now let us compute limit x tends to a of f of x, or maybe I can do it from this above one better. Let us multiply this by h, right. So, we have two things, this is one and the other is that you do this is 0, this is the function f of x is x, instead I am taking the function f of h is h, and this limit is 0. So, if we know from our rules for limits that if you multiply the two functions whose limit at a point exists, then the limit is the limit of the product is product of the limits. So, if you take these two functions and multiply, this is exactly the product. So, that is L times 0 is 0, right. But what does that tell us? That means the limit as h tends to 0 of the function f of x plus h minus f of x. So, I have to be careful and not remember that we know that it is differentiable at a. So, I should have used a here and not x, right. So, my bad, f of a plus h, f of a. So, this is 0, right, and now the term minus f of a is constant. So, this you can add the function f of a to this. So, if you do that, you will get that limit h tends to 0, f of a plus h is equal to f of a, right. But now instead of writing this as a plus h, you could write this as x and just write this as x tends to a, right, because x is equal to a plus h, then h tends to 0 means x tends to a, f of x is f of a. Okay. So, this is a proof that f is continuous at a. Okay. So, differentiability is a much more powerful concept than continuity. So, if it is differentiable, it is definitely at a point, it is definitely continuous at a point. Okay. So, we can now talk about the derivative function. For a function f of x, its derivative function, which is denoted by f prime of x or df dx of x, is f prime x is df dx of x is limit h tends to 0 f of x plus h minus f of x by h. Yeah, the value of that limit at the point x. That's what we mean by the derivative. So, if you do it at different points, you get different values, and that is exactly what the derivative function is. And of course, it may happen that for some points the derivative does not exist. For example, we saw the examples in the previous slides. For we took f of x is let us say the floor function of x, and we saw that at integers it does not exist. But for other points certainly the derivative exists, and so you can talk about the derivative function of the floor function at all points other than the integers. So, in general you can talk about the derivative at all points. The derivative function is defined at all points where the function is differentiable. So, that is the domain of the derivative function. So, let us do some examples. If f of x is x, then f prime x is what? If f of x is sin x, what is f prime x? So, if f of x is x, we have computed what happens for any point. We saw that if this limit that we have gave us the value 1. So, this is 1. So, f prime x is 1. Let us see what happens for sin x. So, if you take f of x is sin x, then we have to compute what this limit is. So, we did this for 0, right. We know that f prime of 0 is 1, we did this, but let us do it for any arbitrary point. So, what is limit sin of a plus h minus sin of a divided by h? That is what we have to compute, limit as h tends to 0. So, let us see what this is. Now, we can use the expansion of sin of a plus h. So, if you do that, this is sin a times cosine h plus cosine a times sin h minus sin of a. Maybe I should put brackets everywhere just to be careful. Okay, so what is this? So, we will break this into two parts. So, you have cosine of a times sin of h by h. So, familiar quantity plus limit h tends to 0, sin of a is common, and then you have cosine of h minus 1 by h, another fairly familiar quantity. So, the first limit this is constant, cosine a is constant because limit is over h, and limit sin h by h as h tends to 0 is 1, that gives you cosine of a. And the second limit, now I think you can do this from our previous computations. Remember, we saw that 1 minus cosine h by h squared, that limit exists and equals half, So, here you can pull the sin A out, and then for the inside limit you can multiply and divide by h, and then you can compute what it is. So, you will get that this is 0, and so the answer is cosine of A. So, when you take the limit when you take this limit and evaluate it, you get cosine of A. So, what does that mean? That means if you take the function f of x is sin x and you compute its derivative, you get the function cosine of x. So, the derivative of sin x is cosine x, and we have demonstrated that with a proof. Okay. So, we will do more properties of the derivative as in the next video on similar lines as we did for continuity, because we can't. So, in this video we have computed everything from what we call first principle. So, we took this limit and then we evaluated and so on, but as we saw for continuity as well, we do some limits and then after that we keep using properties, right. We use the rules for continuity. So, the same kind of idea we will first describe. We will describe the rules for derivatives and then we will use those to compute more limits, more derivatives. So, before we end, let us look again at these examples. So, why did we do all this? We were studying tangents and we came across these two examples which gave us some pause for thought. And we saw in the previous videos that if we demand that our function is continuous before we start talking about tangents, then we can get rid of this example. But this function graph of y is mod x, here we still continuity was not good enough to throw out this example. Now, let us ask what happens for differentiability, and for differentiability we saw that at 0 this function is not differentiable. So, we can get rid of this function also by making the following hypothesis. We will talk about tangents only at points of functions where those functions are differentiable. So, we will gladly talk about the tangent to this function when the point is not 0. For even for mod x, when the point is not 0, we will talk about tangents, and as we saw in, if you remember our video about tangents, we did not have a problem. The problem was at 0. So, we will talk only at about tangents for points where the function is differentiable, and that is something we will study also in the next video. Thank you.